Okay, so let us continue. Our next speaker is Kalyan Chakraborty from the Harish Chandra Institute and Kerala School of Mathematics, and he will speak on the Fourier coefficients of set and Hilbert modular forms. So please.
Yeah, thank you, Professor Bilu, for introducing me. And so let me begin by wishing Professor Balasubramanian a happy birthday, even though it's a couple of days late, but still, it's a privilege to be here and celebrating this elite conference that the organizers have, put in front of us, and almost all the number theorists, as I see, are here. So it's really a true tribute to Professor Balu, and I am one of those privileged ones who got the company, got the suggestions, guidance. Professor Balu was always there for all of us. The number theory school that we see in India, most of them are direct students of Professor Balasubramaniam or being blessed by Professor Balu. So I was there in his 60th birthday also when it was celebrated at HRI. And so I thank the organizers for really giving me this opportunity. It's a true privilege for me to be here and speak on couple of works that I recently did with my students. And with this little thing, let me begin. So the title of my talk today is on certain Hilbert modular forms, Fourier coefficients. And so this is the way that I have arranged the talk today. It's a little bit of motivation. I'm sure there are quite a few students, and so it's for them. And then I'll talk about the fundamental results. So by the way, this is the talk is based on two works. First one, the fundamental result, and the first application that I'll talk about of the fundamental result is jointly with Rishabh Agnihotri, and this has already appeared in the Ramanujan Journal. And the second application is a part of another paper which is in communication with Rishabh Agnihotri and Krishna Arjun. Both of them are my students. So that's the plan today. So let me begin by giving some motivation to the younger people who are here in the audience that about the coefficients of these modular forms. They're very surprising objects. And so they carry a lot of a wealth of information. These modular forms have Fourier expansion, and these Fourier coefficients carry analytic as well as algebraic, lot of information about the form, the particular field that one is working in. Like the Fourier coefficients of Eisenstein series that were calculated by Hecke and Siegel. They're instrumental in the study of these special values of zeta functions in negative integers. That's just one example. And the Hecke operators, which are the operators in the space of these forms. So the action of those operators on the Fourier coefficients goes back to Mordell, and it allows. It's a surprising thing that allows one to show that the Mellin transform of an eigenform is an L function which is having Euler product. So this is an Euler product which we expect if you want to call a L function is a good L function to have it. And of particular importance in the study of modular forms, it is and its various generalizations. So we'll talk about one of these generalizations of the classical modular form is the L function. Because these L functions, they capture, they are formed via these Fourier coefficients. And the analytic properties of these L functions, which is one of the study that Professor Balasubramaniam is famous for and has done a lot of work in that area, the analytic properties of zeta functions. And so they're closely tied up with the arithmetic of these coefficients. So there are these algebraic informations because you'll see there the coefficient will capture the invariance of the field that one is looking into. And these analytic properties also are closely tied up with these coefficients. So Ramanujan conjecture that provides bound on the absolute values of these Fourier coefficients of a cusp form, but it's absolute value, so it doesn't provide any information about the the signs of these coefficients, that how they vary, and which is crucial in many aspects, that how these signs change. And in fact, a remarkable result of Kowalski and his colleagues states that in case of classical modular form, at least, the signs of these Fourier coefficients uniquely determines the form in some sense. There are many other usage of these signs. If you can prove there are infinitely many changes of sign, then it helps in many aspects. So this is one result that I'll be talking about, the changes of sign. And the another one is the well-known bound that's called Sturm's bound. So we want to know that, how many coefficients one has to know to really conclude something about that form, whether it is non-zero, whether it is equal to another form, or whether the coefficients are divisible by certain prime or not. So this is what is called Sturm's bound, which says that, I'll come later explicitly, I'll say, that certain number of Fourier coefficients determine, in fact, the arithmetic nature of the form. Okay, so this is a little bit of motivation about the coefficients of these classical modular forms and its various generalizations that we know. So I'll be talking about one generalization of this modular form is called the Hilbert modular form. Okay, so for me, F will be a totally real field. Okay, so totally real field of degree n, it will be fixed. It's a number field over Q and of degree n, but it's totally real. So all its embeddings are real embeddings. And I will be denoting this OF to be the ring of integers of this field F. So let's take these embeddings to be sigma 1 up to sigma n of F into R, totally real. So there will be only these real embeddings. So thus F can be embedded inside Rn by this natural map. X to this, apply these sigmas. And so this F can be embedded inside Rn in this fashion. So let us, so these are the notations that I'm fixing. So H denote the narrow class number of F. So narrow class number is similar to what is class number. So it is IK mod PK plus. So IK is all these fractional ideals that you take it. And then you quotient it out with the ideals, which are fractional ideals, which are generated by a single element, the principal fractional ideals. So that's the usual class group, and the order of this group we call class number. So narrow class number is simply we take all the totally positive principal ideals. That means the element which will generate is totally positive. That once you go to the real with these maps, so it will be a positive number. So that is what is narrow class number. So we'll be dealing with this narrow class group. And so H will be denoting, again, one can show that it is finite. And H will denote the narrow class number. So H number of cosets are there. It's the quotient group. So let's say that Ti, so these notations will be throughout there. I equals to 1 to H is the number of, this is a class number, narrow class number. So this is a complete set of representatives of this narrow class group of F. So Ti, so there are H is the class number, narrow class number. So this many representatives will be there for each cosets. So there will be this integral, so the ideals, whenever I talk about integral ideals, they are inside OK. And if I talk about fractional ideals, then it is the usual definition. That's a OK module, and I know the definition. So corresponding to each integral ideal n, let me call it, and each representative Ti here. So we have always, we have a congruent subgroup, gamma I n. So this is the I, that is the ith representative that I have chosen of GL2F. And this is the shape of this gamma IN. So these are some facts which I'll be noting before really going ahead. So this will be like A, Ti inverse, B. So here A will be in the ring of integers of F. B is coming from the different ideal. So different ideal is a integral ideal. And so this is the inverse of one fractional ideal, which contains OK. So this is different. This is another invariant associated to the field F. So it's the different ideal. So B is from the inverse of the different ideal. That means from that particular ideal whose inverse is DF. And C is coming from this N DF. D is in OF, ring of integers, and AD minus BC is OF star. So this is the group of unit. OF star is non-zero thing. So A, Ti inverse B. So these are the representatives of this thing. So they will be coming from this various things that are associated with various terms that are associated with this number field F. So this is the different ideal. So we have to remember that gamma IN. So IN is an ideal. So this will be the label that we are talking about. And the shape of this gamma IN is this. So now we have this natural embedding sigma I, prime S of F into Rn. And so we can embed GL to F into this J equals to 1 to N, GL to R. That's the natural one. So whenever if gamma is Aij is in GL to F, so gamma, sigma 1, sigma 2, these are the embeddings. So it will be denote, so this will denote the matrix Aij1, Aij2, etc. So this is in the product now. So each is coming from one of these GL to R. So that will be the conception where your Aijn is simply sigma M Aij. This M will be the mth embedding that will be indicating. So we take gamma in GL to F, and K is K1, K2, Kn. I'm not taking its equal, any K in this positive integers. And so this will be the weight of the form that I'm going to define. And Z is tuple, like in Cn, Z1, Z2, Zn. And for a scalar, so we denote this determinant of gamma. Before I go to the definition of Hilbert modular form, I'm just defining the notations. So determinant gamma, as we expect, it will be determinant gamma, sigma 1, sigma 2, up to sigma n. And Cz, this is the script Z that is written, will be C1, Z1 plus D1 up to Cn, Zn plus Dn, where your Ci is at sigma ic and Di is at sigma id, the ith one, and for Cd in the field F. And Z to the power K, K, remember it's K1, K2, Kn, so it is Zi to the power Kj, J equals to 1 to N. And gamma K will be, take all this gamma Kj and take the product. So I'll be denoting K0 by the max of these positive integers K1, K2, Kn. So to remember this K0. And AK is simply A to the power, you take this sum here, Kj, J equals to 1 to N. Okay, so this is the notations that I need while going ahead, defining what is an Hilbert modular form. So we start with H, the Poincare upper plane, and we consider the n copies of H. And there's an action of GL2 plus Rn via component wise, and each component it is the Mobius transformation that we know. This will be my action for on Hn, GL2 plus Rn. And the classical modular form, this is the definition that classical modular form of weight K on gamma In, this is a holomorphic function from Hn to C. And such that I know it, when you apply this gamma on Z, it transforms like that. The symmetries are like that. This is determinant gamma to the power minus K over 2, Cz plus D to the power K f of Z for all gamma in gamma in. So again, space of such forms of weight K and level N. N is this ideal, remember, or Gothic N, whatever you call it, is denoted by Mk gamma In, standard notation. And actually, if you are not taking Q, F is not equal to Q, then the usual requirement of holomorphicity at the cusps is not needed for Hilbert modular form. So there's something called Kesher principle, which assures that it always has that. So this is a classical modular form definition. And such a function f has a Fourier expansion of this form. C of psi, x trace of psi z. So I'll just define. Here x is the standard notation, e 2 pi ix. And trace is simply you take the sum of all these embeddings, sigma j theta zj, psi zj. And so the summation runs over 0 also, and the totally positive elements of this. So totally positive means, as I told you, that the psi are totally positive, that when you go to apply this embedding, it goes to R and it should be positive. Okay, and in the Fourier expansion, if the constant term is 0, not there, then it is called a cusp form. Okay. So now you remember the H is the narrow class number that we had. So if I have I between 1 to H, and for each of them, I can define a classical Hilbert modular form of a fixed weight K for the congruent subgroup. And then there is a notion of Shimura, which associates this H tuple, F1, F2, Fh, the classical one, weight K, on this gamma I n, an adelic Hilbert modular form F. And this adelic form, so this tuple H will be associated to one of these adelic Hilbert modular form. And it is well known that this is an automorphic form on GL to AF, where your AF is the adel ring of F. Adel ring, people who are, young students, it's just the restricted product of the field with take it completion with respect to all the evaluations, some restrictions. So this is the language which helps you, associating with a lot of other arithmetic, and can help you to prove many results, which otherwise might be difficult to do it for individual classical forms. So this will be my notation for the space of adelic Hilbert cusp forms of weight K and level n. They will be denoted by Sk, this n, similar notation. Now there is one natural question will be there. What is the relation? So a CMF will be the Fourier coefficients of this adelic cusp form, that Hilbert cusp form that I'll be using for F. And you remember that AI psi will be was the Fourier coefficients of the classical forms for each I. So they need to have a relationship between the CMF and this individual Fourier coefficients of the classical form. And this is the relationship. Sometimes I'll be writing CFM. So just sometimes it is like this. So this is AI psi to the power minus K0 by 2. Remember, K0 is the max of K1, K2, Kn. A norm, the usual norm of this integral ideal M over K0 by 2. So that's the relationship. And so for each integral ideal M, that's what it holds. Where M has some form, psi, Ti inverse, you remember, Ti is one of the representatives of those H classes that we had for the narrow class group. For unique I and for some totally positive element psi of F. So that's what M will turn out. So this is the relationship between this Fourier coefficients of the adelic Hilbert form, modular form, and for the classical ones. That will be utilized. Okay, so this is the setup that I wanted to put in front of you, and I'll be working in this setup. And the fundamental result that was in the introduction I was talking about is this fundamental result. And the main part of the talk is an application, 2 applications, in fact, of this particular result. And so this is the first work that I was talking about with Rishabh Agnihotri, and this has appeared in Ramanujan Journal. So this is the result, and I'll not be going into any kind of, I'll be using this result to show in front of you 2 applications of this result. So F and G are 2 adelic Hilbert primitive cusp forms. So they are Hecke eigenforms, normalized Hecke eigenforms. So suppose f is a positive smooth, what is called the cutoff function, as a nice function, which has support on half one, this closed interval. So f will be always this f will be always for this smooth positive cutoff functions that will be used. And x is totally positive. This is the notation for totally positive. So f and g are two adelic cusp forms, Hilbert cusp forms. This is a smooth, positive smooth cutoff function. And this x is totally positive. Then for any c, if you take it from half and one, and for every epsilon positive, so there are possibilities that you have f is equal to g and f is not equal to g. So if f is g equal to g, so then always there exists a constant a f. This is the form that we are talking, f is equal to g now. And this is the cutoff function that will be mentioned, bigger than 0, such that I'll count this. This is just to tell you that, we are looking into the square-free integral ideals. So these are square-free integral ideals. Square-free means, you have this integral ideal, then you have this unique expansion, unique factorization in terms of prime ideals. So no prime, the exponents are all 1. So that's what square-free, the usual generalization of square-free integer. So this hash indicates that these are square-free, and this simply means that it is generated by MNN. So the absolute value of CFM square, and this is the cutoff function. So I have this constant times x, and this is big O of, so we have to, this norm of this n, the level comes up here. This k0 is the maximum k1, k2, kn, and n is that degree of the extension that we had. So this is the result for when f is equal to g, and when f is not equal to g, then CFM, CGM, again this f of norm of m by x is this. There is no constant term here. The AFF doesn't appear, so it's big O of this. So x to the power c, I just want you to look at these exponents a bit, because this will be will be used in the later part. And here the implied constant depends only on epsilon and the field that we are working in. And also one can show that this AFF is bigger than k0 n, this norm of this n to the power minus epsilon. Again, here the constant will be depending on this field and the epsilon. Okay, so this is the fundamental result that we'll be using to get some interesting information on the Fourier coefficients of these adelic Hilbert forms. As I was telling, that the hash, this indicates that the sum is over square-free integral ideals, and this will be denoted by, to show that that's generated by M and N. Okay, so the first, I go into the first application. So as I was telling you, one of the classical problems is to determine a modular form by a subset of all the Fourier coefficients. So that's like a Sturm kind of bound. So the most talked about result in this case is, as I was telling you, the Sturm's bound, which states that there exists a positive constant lambda, such that if AFN is 0, n up, all up to lambda and k is the weight, and then the function, then the form is 0 in fact. So you have to check only this many Fourier coefficients to conclude whether the form is identically equal to 0. The same thing can be transformed into two, different, in the same question that it take two different forms, and you want to check that when they are equal. So if AFN and equal to AGN up to that, then you are sure that these two forms are identical. Okay, so this is a very useful criteria to have. And a similar question would be that, as we are talking about a subset of all the Fourier coefficients, so square-free Fourier coefficients. Now, how many square-free Fourier coefficients are required to determine a modular form? You can guess that we are going, if the fundamental result you remember, the sum was over the square-free integral ideals. And so in this direction, for classical modular form, this answer was given by Anambi and Shomodas. And I'll come to that result. So it was so the question is about how many square-free Fourier coefficients you need to conclude about the Sturm kind of result for classical form. So that was answered by Anambi and Shomodas. And they used prime number theorem for L function associated to this primitive cusp forms and obtained an upper bound, which was exponential, in fact, in nature. But then later they improved the previous paper, the upper bound, and they used Rankin-Selberg L function for primitive cusp forms. This is that we also will be using for primitive cusp forms. And they proved, so this is by Das and Anambi. So n is a positive integer and chi a Dirichlet character modulo this n with conductor m chi, such that n over m chi is square free. So that's the setup. N over m chi is square free, and take any form in Sk n chi, which is non-zero, and fix an epsilon bigger than 0. Then there exists a square free integer n. So this is the bound. K to the power k is the weight 3 plus epsilon. N is that conductor. 7 over 2 plus epsilon. 7 by 2 plus epsilon. So you have to check up to that, such that AFN is non-zero, where the implied constant depends only on epsilon because it's a classical form. So that's how. I mean, AFN is 0. To check that whether the form is not 0, you have to go up to this. And if if it's non-zero, then you will find Fourier coefficient AFN for this n, which is non-zero. Because this was the classical result, which is not too long ago, and it was by Das and Anambi. And so we considered the same problem for Hilbert modular forms, for those those adelic Hilbert modular forms. Okay, so the setup has to be little bit. Let's remember that this is a non-zero, this adelic Hilbert cusp form. This is our weight, square free level. Now I have square free level. I just explained that in the unifactorization, no exponents are all 1 for the prime ideals that you have, and this is an integral ideal. And so this is the norm of this integral ideal that we're talking, and K naught, as we have decided, that it's the maximal and the maximum of this K1, K2, Kn. So this is the result. That we take adelic Hilbert cusp form, non-zero, with these Fourier coefficients, CFM. Then there exists a square-free integral ideal, M, with the norm is bounded by this K naught. K naught is the maximal, maximal of these things. 3n plus epsilon. Norm of this integral ideal, 6n square plus 1 over 2 plus epsilon. Remember that was 7 over 2 for them. Such that CFM is non-zero. And here the implied constant depends on epsilon certainly, and also on the field F over which this is a totally real field of degree n of extension degree n, and over which we are considering this adelic Hilbert cusp form. So this is a generalization. Is a generalization of the result of Das and Anambi for Hilbert modular forms. Okay, so I just give a brief idea how it's a brief. The main in the paper, the main work was there to really prove that fundamental result, and this part is not so technical. So I thought of giving a little bit of flavor. So this is the Rankin-Selberg L function, F for tensor G. So F and G are two primitive cusp forms in SKN, and we consider this Dirichlet series. So I'll define what is zeta Fn 2s CFM CJN by, we have taken two primitive plus forms and we are considering the separate norm of m to the power s. And so this part I'll just define in the next year thing. And this part I'm calling RS F tensor G. This is an L function that I'll be considering. And another one is Ln. This is the level that we are talking about, S F tensor G. So this is for P dividing this particular ideal, 1 minus NP, one factor. Another factor is alpha I P beta J. So this alpha i's and beta j's are the roots of the quadratic polynomial standard one, which is like x square minus this P at Fourier coefficient count plus psi P comes there, psi P 0 or 1. These are the roots. So there are two of them, F and G. So alpha 1 and beta 1, alpha 2 and beta 2. So this is my Ln. And LB, so these are few, I'll give the relationship between them. This is a bit of work that I've gone through in the paper. So LBSF tensor G is 1 plus CPF CGF and norm P to the power minus S. This is same as, again, the hashes for that particular notation that I defined, CFM CGM by N, M to the power S. These are the three L functions, where our zeta Fn is simply the Dedekind zeta function in the field that we have, zeta F2S, and take all the ideals that divide n, so 1 minus n norm of that ideal to the power minus 2s. So this is zeta Fn for me, and Rs F cross F tensor G is the rest of the L function. The next term is there. Okay, so this is my zeta Fn. And this is the following relationship between the above this Dirichlet series that we have defined. So Ln Sf cross G, some work is there. So it is L S F cross G, F tensor G times some nice Dirichlet series, which is absolutely convergent for real S bigger than half. So this Ln S F tensor G is same as LS F tensor G times a nice Dirichlet series, and L to the B S F tensor G is simply Ln, and Ln already I know. So again, I will have this HS there, and so Fs and Hs are Dirichlet series which are absolutely convergent for this plane. So that can be shown. So let us define this L infinity, another one. I'm coming to this a result of Shimura. So L infinity S F tensor G is this gamma product of the gamma factors with this power of this pi comes there. And then let us denote by delta lambda S F tensor G is this. So I have this norm of this different times that integral to the power S, this L infinity is there. And then I have this LS F tensor G, the main, the Rankin-Selberg thing that I had mentioned in the first. Then this, so if we consider this lambda S F tensor G, this particular series, then we have this result of Shimura, which states that this admits, this lambda S F tensor G admits an analytic continuation to C. It's an entire function if F is not equal to G. And if F is equal to G, it has a meromorphic continuation to the whole plane with possible simple poles at S equals to 1 and S equals to 0. Okay, and at S equal to 1, Shimura gives the residue of this particular L function. So this is a group of units, OF star. So this is the result that one will be using. This residue also one will be using at S equals to 1. So this function is nice, and it has either it's an entire function or it has a meromorphic continuation, except these two maybe. And at S equal to 1 also he gives the residue. So this is Shimura's result. Okay, so this is the background that is required to prove that particularly I think how many square free integral ideals determine a form. The similar question that Das and Anambi had answered for classical forms. So we need, so there is a similar new form theory for Hilbert modular forms that will be appealing here. So this F1, F2, Fm. So this is the basis for the space of new forms. Let weight k and level dividing eta for n for skn. Then if I take a f which is non-zero in skn, then this new form theory tells me that f is actually, you can get it through these fi's by the slash operators. So I equals to 1 to m. This is this for each of them. aiq, I'll come to this fi stroke bq. So I'll just define what is fi stroke bq. And these aiqs are zero if fi is not a new form of level n by q dividing n, so n over q. And the stroke operator, that shift operator that is called f stroke bq, is simply n of q to the power minus k naught by 2, and f you apply this 1, 0, 0 q inverse. So in fact, it maps skn to sknq. So mq inverse, cfm becomes mq inverse, in fact. So, so here this is adel, I think the q such that q infinity is 1, and q of q times OF is in fact this this ideal q that we get back. This is a well-known the shift operator. So you start with any form, Hilbert adelic Hilbert modular form, Hilbert cusp form. Then through this basis, you can write this f in terms of this particular basis. So let us take an ideal q naught which divides n, the ideal that in the level that we have started with the property that norm of this q naught is less than equal to norm q prime for any ideal q prime, which is not q naught, dividing the level, and this ai q naught is not equal to 0, minimal in some sense for some I. So this is the q naught that one will be working. So remember, this is an ideal with the property that norm of this will be always less than equal to norm of q prime for any other ideal dividing that level, and correspondingly ai q naught is not 0 for some I. This is it's minimal in this sense, q naught. Okay, so this is 4. So let me go to 44. 4 is that a new form theory. So I'll be comparing the coefficients here. So comparing the Fourier coefficients indexed now q naught m. Q naught, remember, this is q naught that we are talking about. Square free ideal co-prime to the level n. So what we get is cf of q naught m. So I'll be interested into this particular q naught times m is simply aiq fi. Fi is each of those basis elements q naught m by q. I equals to 1 to m. This is that basis. And look at all the q's that divide n. And then I will have cf, that q naught m level is aiqc of fi q naught m by q. So this is just by comparing the coefficients. So we need this. So here you note that the norm of q is less than norm of q naught. If suppose this happens, that you get a q which is less than that q naught, then this is 0. That's what the definition was there. And also if q not equal to q naught, then this is 0. Okay. So for some m, so out of this we'll get some r number of them. Not all of them will survive. This will in fact become I equals to 1 to r ai q naught cfi m. Okay, that's by this little argument we can get from here this you think that what are the coefficients that will be surviving, looking into that fact. So this is the thing that will be required for us, that cf q naught m, q naught with that particular property is ai q naught cfi m, for some r up to n less than equal to m. So now let us define this object S, which is, remember we had the fundamental result talks about some bound of this. So we define S is CF, this Q naught M the square, and then the cutoff function Nm by X, F Nm by X. Let's define by S this one. So now just go ahead and just separate it out. So it's AI key not C of n, take the bar of that one, do a little bit of this calculations, and then you can separate it out with I equals to 1 to R, the square, CFIM square, F, and then the bars will come here. So this can be written as this plus this, just separating it out. And now we use the fundamental theorem, because that theorem gives us the bound for this CFIM square, this part. So we use that one. And this AFIF comes up here, because here we have separated it out in that fashion. And remember, this is the exponents of K naught is the maximal element in K1, K2, Kn, it comes out there. Okay. Now here you want us to just apply now Cauchy-Schwarz inequality, and the bound on R. R is that, this dimension of the space, Sk n by Q naught. We just put it here, and we can get from this inequality, this S is bigger than this AI Q naught square times this part. So just I have to use Cauchy-Schwarz here and use the estimation for the bound here for the n by Q naught level. Now, since here, this is independent of the choice of, you see here, choice of that particular cutoff function f. So we can choose as whatever is convenient for us. We choose in such a way so that f is between 0 and 1. And this CF Q naught m absolute value square, norm of x between x by 2 and x, is bigger than equal to this particular term. Now I have to just choose. I have to choose my x and the c properly, so that the right hand side becomes positive, and I have the result. Right? Because it is CF Q naught m absolute value square is what I get. This part is positive. So that's how it has been. It's been proven using this ranking server and using this fundamental result that I had quoted in the beginning to get how many Fourier coefficients, getting some bound on some form of a number on the number in terms of the norms that you have to check, so that to check the form is non-zero. So this is the first application that I wanted to show you. And the second application is about the changes of sign changes of the Fourier coefficients that I was telling you. So this work contains, this is a part of that one, and also in some form of arithmetic progression, because you remember we are talking about the narrow class group. So we have defined the arithmetic progression by taking each coset of this. It's just somewhat generalization of what we have arithmetic progression in terms when we have integers, similar to that. So this is one result, and the other result I'm not coming. So that is an arithmetic progression. So this is about, this is a joint work with Krishnarjun and Agnihotri. This is in communication. So again, F is a primitive adelic Hilbert cusp form, as we have defined, with this weight, and level is an integral ideal, n. Then this sequence, these are the Fourier coefficients, you remember. CMF has infinitely many sign changes, where m runs through the square free integral ideals of f. Okay. So so whenever you say infinitely many, so can you get some kind of a quantitative result? So the number of sign changes in CMF, if you this is the natural bound that you will put, it is at least x to the power half for large n of x. So this is a result which I will again want to give a little flavor of that before I end. Okay, so infinitely many sign changes, and at least that many sign changes will be there if you bound your ideals that over which is varying up to x. What is the strategy? Strategy is compare the growth of these two sums. So this already, as I told you, this is the fundamental result. that the square of the Fourier coefficients, norm up to x, and again, this hash will indicate that part, that over square-free integral ideals, this sum is varying. And for CMF. So this was already known by the fundamental results. So this is what is unknown. So this paper contains an estimation for this. So to get an estimation of CMF, we define what is we call it SQS, CMF by norm m to the power s. Again, m is running over the square-free things, and we have this product over prime ideals now 1 plus c PF by np to the power s. It's a nice function. Now, if we apply Ramanujan bound here, which is a known result here, that CMF is norm m to the power epsilon for depending on epsilon, then we can show that this is absolutely convergent for real s bigger than 1. So by using Ramanujan bound just here, one can, with little bit of work, very little work, one can show that this SQS is absolutely convergent for real s bigger than 1, but we want a little more. So in order to proceed further, we want we show that, in fact, this can be analytically continued to the region real s bigger than half. So that's the next target. Okay. So with this in mind, to this end, we let us define this dr, this goth rs, again, some ideal will be there. So take all the CMF by n m to the power s and take all the divisors of this ideal divisors of this m, and then this is same as, this CRMF by NRM to the power s. So this is my DRS. And then a little bit of work, one can easily show that SQS is in fact, SQS, remember, this is the thing that we want to, so SQS is for me this, CMF by NM to the power s is the product. So this mu function is the same way you can define as you have for mu for the integers. So again, you look at the all the prime divisors of this one, and if all of them exponents are 1, then -1 to the power the number of those ideals and 0 otherwise. So from here, one can show that using this, that SQS, the term that we want to show that it is analytically continued from this half, real s bigger than half onwards. So SQS can be written like this. And suppose if we define our SPS, this P is CPF square by NP to the power 2s, and their psi star is simply the idelic version of what is called the adelic Hecke character. So not going into that one, norm P to the power -2s, and CPF by N P to the power s plus 1. Suppose I define SPS by this. Then this is some work to show that SQS, in fact, LSF times, product over all primes, 1 plus SPS. So this is the benefit of that one. And here on the right-hand side, the product on the right-hand side is absolutely convergent for real s bigger than half. Okay, so that's the upshot from here, is that SQS has an analytic continuation to the plane real s bigger than half. Okay. So we are able to show that one, that it is absolutely convergent. It's you can analytically continue it to the plane from real s bigger than half onwards. So how does that help? That helps us using, again, not going into the details, by some slight variation of Perron's formula, we can estimate this sum, which was our target, to get an estimate for CMF, where the partial sum that norm up to x, and with square-free ideals. So we can show that it is big O of x to the power half plus epsilon. That was the target. Similar to that, what we have. And already we had from the fundamental result, we know that C square MF is AFX plus, again, x to the power half plus epsilon. So these two are there for us. How does this to help us to get the sign changes? So there is a result of interesting result of Meher and Javan Meher and Ramurthy, which states that it's for any sequence of real numbers, satisfying that an is big O of n to the power alpha, such that your an, this partial n up to x, is x to the power beta, and n square is cx times O x to the power gamma. This is similar to what we have here. for CMF and C square MF, where alpha, beta, gamma, and C are non-negative constants. And if alpha plus beta is less than 1, then for any R satisfying in between this max of alpha plus beta gamma is the max, and in 1, the sequence has at least one sign change for n in this interval, at least one. And in particular sequence has infinitely many sign changes, and the number of sign changes for n, the bound is also given, x to the power 1 minus r for sufficiently large x. Now you can see that we will be applying this one. We have all this data with us to get the result. So we can take alpha equals to epsilon, beta gamma equal to half plus epsilon that we have there. So it will become 1 minus half, and x to the power half, it comes at least so many. But how does the proof go? A brief before I conclude. Suppose on the contrary, suppose we have only finitely many negatives. So without loss of generality, we can assume that there are only finitely many negative terms, CMF are there. So therefore, if you go to a large X, you'll have all positive things there. When your NM is, let's say this interval x to the power r, where r is, less than, is maybe other way between 1.5. So we have this result already from our previous discussions, and the fundamental result tells you the other way around, that r is bigger than half. We have x to the power r is less c square mf. That gives us the contradiction that this thing that we have started with, that there are only finitely many. Okay, so this way, and so using this Murthy-Meher, also one can conclude that there are infinitely many sign changes. So that is what is there for me today to speak to you. And this is this references that I was talking about. This is Das and Anambi, and this is some long back I did with Yanis Petritis. So this is the Koal Swiss Ramurthy and Ramurthis, and then we have this. These are the few things that are being used in this particular talk. Thank you for your attention. Thank you so much.
Okay, thank you. Thank you. And are there any questions? There were many questions and comments during the talk. Well, I did not want to interrupt the speaker.
Yeah, let me see if I can.
Yeah.
There are.
Now maybe some people, it seems that they've successfully answered more or less all the issues already in the comments. Maybe there are still some more questions. Maybe Zeev, you have a question?
Bill is in the mail. Bill is in the mail.
What's in the mail? Zeev is there. Some questions from Zeev, that would be interesting. So you have sent me some mail, Zeev, or?
One question is for the number of sign changes. This is just a lower bound. What do you think is the truth?
Yeah, that is a good question, but I don't know. This is just the bound that we get from there, but the truth, I mean, can one improve that one, or sharp or not? So that part is not known to me. Maybe you know, so you have some ideas.
Known over the rationals for classical modular forms? I thought there was some sharper results available there.
Sharper than Sturm's one?
Yeah, are there is there anything sharper? I thought sound had done something. I just don't remember.
Sound, maybe, yes. Yeah, I remember seeing something that's improving that particular bound. Yeah, so that's a good query. Maybe one would try to see if one can improve that. Yeah, no, I just doesn't come to my mind right now. If in the audience someone can answer.
Okay, there is Akash Sinka Roy who wants to ask a question. Please,
sure.
Please
unmute yourself. Yeah, you can unmute yourself, Akash.
Unmute yourself, please.
He's muted.
Hello, sir. Thank you for the beautiful talk. Sir, so I just had a small question about Theorem 3.
Theorem 3 was talking about that sign changes, huh?
Coordinator.
Okay, so let me go into Theorem 3.
Yes, sir. I think so. Yeah.
No, that was
non-zero, like C or M.
okay.
So it's just.
This is Theorem 3. Yeah.
Okay.
Yeah, Akash.
Yes, sir.
Yes.
So just wondering,
Your voice is
Breaking, yes. No, can't
make
understand.
maybe phone around.
Idea depends on f and epsilon. So do we know what the? Sir, can you hear me now?
No, yeah, okay. Let's go ahead. Try.
Yes,
No.
sir. So I was just wondering, is it possible to make explicit the dependence on f and epsilon in the bound?
Yeah. So our method really doesn't give that one. So to make it explicit, maybe you have to really go back with all the estimation that we are using. Should be possible to do it.
Okay.
But I don't know. This work that we have done it, we haven't tried to really make it explicit. So, and I'm should be possible if you go back the estimation that we are using for other Dirichlet series and other things. So may not be that easy though.
All right. Okay,
But
sir.
yeah,
Thank you.
I mean that's another work that one has to do really.
Nice.
To make it explicit.
Okay, sir. Thank you. Thanks again for the beautiful talk.
Yeah, sure. Thanks.
And well, any more questions? Okay, then let us thank the speaker again. And we restart in 3-4 minutes.
Yeah, thank you so much. Thank you so much.
Thank you.
Yeah, I'll be there.